Hello everyone. So in this course, we are going to discuss about what is called the state space modeling or state space approach of modeling a system. In the undergraduate first level of control systems course, you might have done about transfer function modeling of a system, right? What is transfer function? It is the ratio of Laplace transform of the output to Laplace transform of the input when all initial conditions are zero. So there itself, from the definition of transfer function, one limitation is there. What is that? We need to assume all initial conditions to be zero. So your system may be having some initial conditions, but they need to be dropped off to determine that transfer function. Okay. And when we derive the transfer functions, it is assumed that the system is LTI SISO system. That means linear, time invariant, single input, single output system. But practically, our systems may not be LTI. They may be non-linear systems. They may be having time varying parameters. There may be non-zero initial conditions, and they may be MIMO systems. That means there may be multiple inputs and multiple outputs, because of which transfer function cannot be applied into such instances. And further, as from the definition, transfer function concentrates more on input-output relationship rather than the internal structure of the system. Okay, so these are all some of the disadvantages of transfer functions. Practically all systems are non-linear. Okay, linear systems, 100% linear systems exist only in paper, and all systems in reality are non-linear. Okay, they may be time varying, they can have many inputs and many outputs, and so on. Because of which we need to go for a different way of modeling such practical systems. And by the way, the control theory based on transfer function modeling is called classical control or conventional control theory, whereas the control theory based on state space approach is called modern control theory. So in state space approach, we focus more on the internal variables of the system, which are called state variables. Okay, so rather than focusing on input-output relationship, we focus more on the internal structure of the system through internal variables called the state variables. So we will get into the details. The control theory based on transfer function approach is called conventional, or rather classical control theory. Okay, whereas the control theory based on state space approach is called modern control theory. Okay, so in this course, we are going to focus more about the modern control theory, which in turn is based on the state space representation. Okay, so first let me write the advantage and disadvantage of classical control and modern control. Classical control, and here we have modern control. Okay, what's the first problem? As I said before, it is suited for LTI SISO systems. What is LTI SISO system? It means linear time invariant, single input, single output systems, and is not applicable to, and cannot be applied, or and is not applicable to non-linear time varying MIMO. What is MIMO? Multi-input, multiple output. Okay, MIMO systems. Okay, then second, from the definition, it is clear that if there are initial conditions, they need to be dropped. Okay, so that means initial condition dynamics cannot be included in the transfer function model. Okay, so initial conditions of a system cannot be included. Initial conditions of a system cannot be included in analysis and design. In analysis and design. Okay, because that's evident from the definition of transform itself, ratio of Laplace transform of output to Laplace transform of input when all initial conditions are 0. Fine. Then the transfer function approach focuses on the system output for a given input, and hence does not provide any information about the internal variables or structure of the system. Internal variables or structure of the system. Okay, then the design is carried out normally using trial and error procedure, which means the resultant control system may not be optimal. What do you mean by optimal? Say, for example, you want to move from point A to point B. Okay, there may be many paths, but if the condition is in the minimum time, then you need to follow the straight line trajectory connecting points A and B. Okay, or the condition maybe it should be a minimum fuel consumption. Okay, so this transfer function approach mainly is carried out with the help of trial and error procedure, and hence that will not essentially lead to result in optimal control system. Okay, the system design is carried out in a trial and error approach. And may not yield optimal control systems. Okay, so these are some of the cons or the negative aspects of or disadvantages of classical control. Okay, now let us see the advantages of modern control. So you can be applied to nonlinear, time varying MIMO systems. Okay, then initial conditions can be incorporated in this modeling. Initial conditions can be incorporated in this modeling approach. Okay, then this state space approach, as I said before, is based on some internal variables called the state variables. Okay, so the state space approach is based on certain internal variables certain internal variables called states state variables. And the advantage is that at any time this can be known. At any time we can know the states variables are known. The states are known. Okay, internal variables is based on certain internal variables, and these variables at any time, and these variables at any time can be known. These variables at any time can be known. Another advantage is that from the state space model, we can have a discrete time model which can be analyzed with the help of a digital computer. Okay, suppose you want to implement control system in a digital computer, then we need to have a discrete time model which can be easily had from the state space model. From the state space model of a system, from the state space model of the system, a discrete time model, can be obtained, which can be analyzed, using a digital computer, Okay, and as the last point, so as using this state space approach, the optimal control system can be derived for a given performance index. Okay, using state space approach, using SS state space approach, a system can be designed for optimal conditions. With respect to given performance indices. Okay, so when you want to design an optimal control system, it is better to have the system modeled in state space form. Okay, so in short or in brief, so as a point I can write, in short, the state space representation focuses. The state space representation focuses on the internal structure or preserves the internal structure, whereas preserves the internal structure. Of the system. Preserves the internal structure of the system, whereas the transfer function modeling focuses only on external relationship between the model output and input. The model output and its input. Okay. The model output and its input. Fine. So we will now see what's the formal definition of a state. Okay. Formal definition, state. The state of a dynamical system, is the minimal set of variables, that's very important, okay, is the minimal set of variables such that a knowledge of these variables, at t equals t naught, that means the initial conditions. Okay, that means the initial conditions. Together with the knowledge of inputs, together with a knowledge of inputs, completely determine for t greater than or equal to t naught, completely determine the behavior of the system for t greater than or equal to t naught. Okay, so along with initial conditions, okay, so what state means they are the minimal set of variables, so that a knowledge of these variables at equal to t naught, that means initial conditions. So knowledge of initial conditions together with the knowledge of inputs can completely determine the system behavior for any time greater than or equal to t. That is what is called the state variable. Okay. Now, what is state space? State space means the n-dimensional space. Okay, state space. The n-dimensional space, the n-dimensional space whose elements are state variables. Are the n state variables is called state space. Okay, so any state. Okay, what will be any state in the state space? How can represent a state? By a point. Okay, so any state will be represented by a point in the state space. Any state can be represented by a point in state space. A point in state space. Okay, so this is the formal definition of state and state space. Okay, now let us look at the concept of state and state variable. State variable. Okay, so we have an LTI system like this. Okay, where u of t is the input and y of t is the output. Okay, so in transfer function approach, what will we do? We will convert everything into S domain. We will take the transfer function of the LTI system and represent that with g of s. Okay, this is the transfer function. So here we have u of s and here we have y of s. Okay, so what is y of s? It is nothing but g of s into u of s. So how will you find the response? Time response is L inverse y of s. So that means L inverse y of s, or that means L inverse g of s into u of s. How will you find the L inverse of this thing? Using convolution integral. Okay, what is convolution integral? Integral minus infinity to t g of t minus tau u tau d tau. Okay, this is what you get when you apply convolution integral. Okay, integral minus infinity to t g of t minus tau u tau d tau. Now this time interval can be split into two, from minus infinity to t naught. Okay, g of t minus tau u tau d tau plus integral t naught to t g of t minus tau u tau d tau. Okay, in this way you can split it into this two components. One is starting from minus infinity to t naught, and the other one is from t naught to any given time instant t. Okay, so what is the first term on the right hand side? That corresponds to it is due to the initial condition. Okay, because it's from minus infinity to t naught. That means the initial condition. Okay, and what is the second term? It is by the virtue of the input signal u of tau. U as the input signal here. U of t as the input signal here. Okay, so the first term is because of the initial condition, and the second term is due to the input signal. Okay, so the output y of t. Okay, what is the left hand side? Y of t. Okay, so the output not only depends on the applied input, but also on the initial conditions at t equal to t naught. Okay, so let me write here. Thus, the first term, on RHS, is the output due to the initial conditions. I see, due to the initial conditions of the system at t equals t naught, and the second term is by virtue of the input to the system, by virtue of the system input. Okay, so the output of the system depends not only on the input signal but also on the initial conditions. Okay, hence the output y of t not only depends on the input applied at for t greater than t naught, but also on the initial conditions at t equals t naught. So this equation I can write like this: y of t equals what? This is some initial condition. So y of t naught plus integral t naught to t g of t minus tau u tau d tau. Okay, so what is the first term? First term is the state of the system at t equal to t naught. You can say like that. Okay, because t naught was the initial condition. Okay, so the first term y of t naught is the state of the system at t equal to t naught, and it is necessary to uniquely define the output at any instant of time. Okay, when an input is applied. Are you getting me? Because if this term is missing, you cannot find. If this term is missing, you cannot get the correct output. Okay, so this corresponds to the initial condition basically. Fine. So the first term y of t naught, the first term y of t naught is the state at t equals t naught, and is necessary to uniquely specify the system output, when input is applied for t greater than t naught. Okay, so the variable that represents this state of the system is called state variable. So here, which is the variable that represents this? It is the y. Okay, it is the output variable y, right? So the variable that represents this state of the system that represents this state of the system is called state variable. Is called state variable. Okay, the state of a system, the state of a system is the summary of complete behavior. It's the summary of complete behavior or complete status. Complete status, that would be apt word. Complete status of the system at a particular time instant. At a particular time instant. Okay, so state is what? State is the summary of the complete status of the system at any given particular time instant. Okay, and the variable that represents this state is called state variable. Okay, thus at any particular time, hence at any particular time, the state of a system can be described. The state of a system can be described by the values of state variables. Okay, by state variables. By state variables. Okay, and state variables need not be physical variables. Okay, and they need not be even measurable also. Okay, so later we will see how if the state variables are not measurable, then we can use it as a state variable. Okay, then we need to estimate that, we need to or observe it. Okay, so if all states are not available for measurement, then we need to design a state observer or a state estimator. Okay, you will see that in the due course of time. Okay, so at any particular time instant, the state of a system can be completely described by the state variables. State variables need not be physically measurable. State variables need not be physically measurable. Okay, and they need not be physical quantities also. Need not be physical quantities. Okay, now let us see how we can define state variables for some physical systems. Okay, state variables for physical systems. State variables for physical systems. So first one is a capacitor. Okay, so we know it's the capacitor representation. So this is plus minus C, this is VC of t, this is current IC of t. Current IC of t. Okay. So what is current IC of t? IC of t is nothing but C into d by dt of VC of t. Okay. Or what will be the voltage? Capacitor voltage VC of t, 1 by C integral IC dt. Okay, from minus infinity to t. Right. So this I can split into two. 1 by C into integral minus infinity to 0 IC t dt plus 1 by C integral 1 by C integral 0 to t naught IC t dt. Okay. So this is similar. So you see here, this is similar to this expression. Okay, this is equation A, right? So you should know the initial conditions, and if you know the input signal, you can determine the state at any point of time. So same is here. Okay. So if you compare that with equation A, you will see that VC of t. What is this thing? This is the voltage at zero initial condition. Okay, plus this is the voltage at time t afterwards. Okay, corresponding to the input signal. Okay, so comparing with equation 1 or equation A, let me mark this as equation A. Comparing with equation A, comparing with A, Vc of t, the capacitor voltage can be chosen as a state variable. Capacitor voltage can be chosen as a state variable. Okay, so in a network having capacitor, we normally choose capacitor voltage as one of the state variables. That's the reason. Okay, now inductor. Okay, so in the inductance, what happens? It stores energy in its magnetic field. Okay, this is inductance L, this is VL of t, and this is IL. Current through the inductance. Okay, plus minus. Right. So, what is the voltage across the inductance? L into d by dt of IL of t. Okay, or what will be current? The current through the inductance IL 1 by L integral VLT dt. Okay, again as before, it can be split into two. One is from minus infinity to 0 and then to t naught. Then to t naught. Okay. Oh, sorry, I will take this to be t naught. Minus infinity to t naught and t naught to t. Okay, I think I made a mistake there. T naught to t, correct. T naught to t. Okay, please note that there was a correction there. This is the initial time is taken to be t naught. Okay, and from t naught to any instant time t. Okay, so again, as before, this can split into two. 1 by L into minus infinity to t naught VL dt plus 1 by L into integral t naught to t VLT dt. Okay, so again, as before, what is this? This is the capacitor current at the initial condition. Okay, and this is the current at any instant of time t. Okay, so that if you compare with this equation with equation A, again we can see that the capacitor current will be qualified to be defined as a state variable. Okay, thus inductor current, not capacitor current, inductor current. Okay, capacitor voltage and inductor current. This was the current through the inductance. Okay, thus inductor current IL of t can be chosen as a state variable. Can be chosen as a state variable. Okay. Now, what about resistance? Resistance is a static element because the output at any instant is dependent upon the input at that particular instant. So it's a static element, you can say. There's no memory. Okay. Whereas inductance and capacitance, they are dynamic elements. They have some memory kind of thing. Okay. That depends on the initial conditions. Whereas in resistance, current and voltage, they are independent of the initial values. Okay. They depend only on that instant, the current or voltage at that very instant. Okay, so we cannot define a state variable for a resistance. Okay, inductors and capacitors are energy storing elements. Energy storing elements. State variables are associated with energy storing elements only. Energy storing elements only. Okay, a resistor cannot store energy. But absorbs and dissipates energy as heat. Okay, so no state variable. So no state variable is associated with air system. Okay, so state variables are associated only with energy storing elements, whereas in a resistance, it will simply absorb and dissipate energy as heat. Okay, so you cannot define state variable for air resistance. Okay, that's about electrical system. Now we will take up mechanical system, translational mechanical systems. Translational mechanical systems. Okay, so we will first consider mass. Okay, we consider a moving mass. So it's a fixed surface, there's a mass m with an average displacement y of t, to which a force f of t is being applied. Okay, so what's the force expression here? Force expression f of t is m d square y by dt square. Okay, or in terms of velocity, I can write m into dv by dt. Okay, so let us consider this velocity term. So f of t equals m into dv by dt. Okay, so what will you get? What is the velocity from this part? This term velocity will be what? 1 by m integral minus e to t m. 1 by m into f of t dt. F of t dt. Okay, 1 by m into integral minus infinity to t f of t dt. Okay, again as before, this can be written into 2. It's split into 2 minus infinity to t naught f of t dt plus 1 by m integral t naught to t f of t dt. Okay, so what is this? This is the initial velocity v naught. Okay, and this gives the velocity corresponding to the input signal f of t. Okay, so what would be one of the state variable here? It will be the linear velocity. Okay, thus the linear velocity of the mass can be a state variable. Okay, linear velocity of the mass can be a state variable. Now, how is linear velocity and a linear displacement related? V is nothing but dy by dt. dy by dt. Or what will be y from this? Y will be integral v dt. Okay, so that means again from minus infinity to t. So I can write like this: integral minus infinity to t naught v of t dt plus integral t naught to t v of t dt. And what is this? This is nothing but y naught or y of t naught plus output or the displacement at any instant. Okay, so that y of t can also be chosen as another state variable. Since linear velocity is the time rate of change of linear displacement y of t, the displacement of mass can also be chosen as a state variable. Okay, that's about mass. The next one is spring. So this is the spring which is connected to a fixed surface. Okay, this is spring constant K. The mean displacement is y of t, and here we are applying a force f of t. Okay, so when you apply a force, there will be an internal restoring force which opposes the applied force. Okay, so what is that force? Fk of t will be what? K into y of t. In a linear spring, the applied force is proportional to the displacement. Okay, K into y of t. Okay, so in terms of velocity, what can you write? K into integral minus infinity to t linear velocity. Is it not? Because v of t is what? V of t is d by dt of y of t. So what will be y of t? Y of t will be integral v dt. Okay, that's it. Okay, now this again can be split into 2. K into integral minus infinity to t naught v t dt plus K into integral T naught to T ddt. Okay, what is this? This is the force, the storing force at T equal to T naught, initial condition you can say. And this is the force at the other instant. Okay, so spring force can also be chosen as a state variable. Thus, spring force can be chosen as a state variable. Okay, so a moving mass stores energy in the form of kinetic energy, whereas a spring which is stretched or compressed will store energy as potential energy. So that is why state variables are associated with mass and spring. Consider a dashboard or a damper. What happens? It cannot store energy. Okay, so you cannot associate any state variable to a damper or a dashboard. Clear? So let me note that point here. A mass in motion stores kinetic energy, and a spring stretched or compressed stores potential energy. Okay, hence state variables are associated. Hence, state variables are associated with mass and spring. Okay, a damper or a dashboard absorbs energy and dissipates. Absorbs energy and dissipates it as heat. Dissipates it as heat. It cannot store energy. It cannot store energy. Hence, no state variable can be associated. Hence, no state variable can be associated with dashboard. Okay, no state variable can be associated with dashboard. Okay, so as a point, notes. Right, first one, for an electrical network, inductor current and capacitor voltage inductor currents and capacitor voltages can be chosen as state variables. Okay, so if you're analyzing an electrical network containing inductors and capacitors, you choose the inductor currents and the capacitor voltages as the state variables. Okay, SV means state variables. For a mechanical translational system, displacement and velocity of mass, as well as spring displacement and spring force qualify to be state variables. Okay, then in general, after writing simple derivative differential simple derivative equation for each energy storing element each differentiated variable can be chosen as a state variable. What's the meaning of that? For example, what is our inductor current? See, what is our inductor current? It was LdI by dt. Okay, so what is inductor voltage? Inductor voltage is, say, VL is L di by dt, DIL by dt. So what's the variable that is being differentiated here? It is the inductor current IL. Okay, that is what's written here. So each differentiated variable can be chosen as a state variable. So inductor current, that is the state variable. So here that's being differentiated. So inductor current can be one of the state variables. Okay, so in general, after writing simple derivative equations for each energy storing element, each differentiated variable can be chosen as a state variable. Okay, so in the next class, we will come up with further details of state representation. Okay, so let me stop here. Thank you.